So this question is path with maximum goal. So given the n by n grid, and you want to traverse a cell. If a cell is empty, that represents 0. So what you need to do is you want to return a maximum goal uh, under the condition. So, so these are the condition. If the current cell is not equal to 0, so you collect the number, which is collecting the goal. From the position, you can only walk one step at a time, and you can only walk left, right, up, and down. So only these 4 directions. You cannot visit the cells more than once. So you can only do one direction. You know, this is one direction. You cannot reverse. Never visit the cell with 0. You can start and stop any cell and then return the maximum. So in this current grid is like this. So you can do like, when you traverse, you can do like this, 586, and then or 68, 586 or 685, like either either direction, or 687 or 786, something like this. But that's not a maximum because the maximum is going to be 789 or 987. So that's the only path. So I just draw like how many paths? So 1, 2, 3, 4, 5, 6, and then definitely 7 and 8. So there are 8 different possibility, or 9, 10, something like this. There are a lot, right? But the point is, we were going to reuse the cells over and over again. So what you need to do is when you traverse, the current path, you want to set the current cell equal to 0, and then you want to reverse, you want to undo the current cell for the next iteration path. So that's pretty much it. And then for this one, yeah, it's pretty obviously it has to be a longest path, so it's going to be like this, right? So 20 is one step by itself, but if 7 plus 6 plus 5 plus all the way to 1 is less greater than 20, yeah, I would take this. Otherwise, it's kind of pointless. So I provide 2 solutions. So first solution is pretty straightforward, just traversing. So every solution is traversing, but in this one is the most easy way to understand. So okay, I'm traversing the 2D grid. Okay, so if the current cell grid ij equal to 0, I don't want to, I don't want to visit, right? So I would say if that is not equal to 0, I would say result equal to max.max, and then keep traversing. Basically, it is. I found the current path. So you can ignore this. So I find a current path. I find a current cell is not equal to 0. I start exploring the path. Okay, explore the path. So I'm traversing the 4 different directions. So -1, 0, 1, 0, 0, -1, 0, 1. Okay, so this is 4 different paths. I will keep updating the maximum for every single path when it's not equal to 0. Okay, so I will have probably int dfx and grid in x and y for current position. So what can I do? I can actually, so this is the original initial value. So I'm going to say grid xy that I will assign to cell, and then later on I will say grid xy equal to 0, and also reverse the xy equal to cell. Okay, and then I also need to declare the path for gold. Okay, I start with 0, and that's pretty much it. And I will traverse directions, and then later on I need to add it, right? So I need to add, so return path gold plus the current cell. So the reason why I start from 0 is because I don't want to assign the 0 right here because it will overlap. So that's why I start with 0. And then when I want to return the path for the gold plus the current cell. Because the current cell should be added here, but again, it actually determines how you build a structure. I mean, how you build a solution. But I start with 0 for the path of gold, and then when I want to return, since I initialize to 0 and then reverse, I'm adding the cell back at this at this line. So anyway, so okay. So when I traverse a 4 different directions, I would say int next x equal to direction 0 plus x. So it's a prediction for the next move. And next y will be the same thing. So I need to make sure this is still within the bound. So if this is less than 0, next x is equal to grid.length out of bound. Next y is less than 0, or next y is equal to grid at 0.length. I want to continue. And again, if the next cell that is equal to 0, I don't want to traverse, right? So grid next x, next y. If this is equal to 0, I don't want to traverse. Otherwise, I can keep adding. So path goal would be equal to path goal, and then depending on how you're going to traverse on each direction, you can say DFS grid, and then it would be next x, next y, something like this. So this should be solid. Yeah, let me run it. Okay. Yeah. All right. So this solution is solid. Time and space all of n times m for this. For this method, all of n times m. For this one is actually all of 4. But however you explore the path, the direction, this could end up all of n times m. So the time for the time at the end will be all of n times m square. So it will be n times m square. So and then the space will be this constant. So space is constant. All right. So in this solution, let's think about this. What happens if a path for gold? So right here. So if I say 987, if I traverse this one already, and then when you traverse this one, when you traverse this path, the different path. So this is the path you already traversed, and this is the path you are currently exploring. So at this point, you find out these two cells. When the current goal plus unvisit goal, if this is already less than what you have for the past goal, then you don't need to keep traversing it because it's a waste of time. You know the current path, this path goal is already more than what you have, so you can ignore whatever. You can stop the risk right away, right? So I probably just copy paste the code and then going through the solution. So okay, so I have a result by default 0 and a return result. I calculate all of the gold. I add everything up. I traverse the row. I traverse the column. I make sure the current cell is not equal to 0. I updating my maximum every single path. If the path is already equal to all of the gold, then I can immediately start because this is a ultimate, the most the most path to collecting the gold, right? So I can return immediately. So I can stop the traversal again. And then for this one, I'm creating, I'm exploring different paths. So grid X, Y, and then current gold for 0. I set myself for this, and then I reset my current cell equal to 0, and then reverse. And my current goal will plus the current cell right away to collecting the gold. And I check my path for the gold. So current goal and path goal are different. And I traverse 4 different directions. I check the next X and next Y, make sure all of these are in the boundary, and also is equal to 0. Then I want to continue. Okay. So if a current goal plus on visit goal, if this is greater than the path goal, then I know I have possibility to collect more gold, right? If this is already less than, if my path, so this is path, if this variable path goal is less than, I already know whatever this guy keep traversing, they cannot collect more gold than me. So I would just say, I'm going to break out the for loop right away. So, okay, let me continue. So current goal plus unvisit goal is greater than the path goal. Then I can come here, path goal, and then exploring the path to keep counting the current goal, and then comparing to the path goal. And then I reset the cell, and then I return the path goal plus a cell. So current goal can add a cell, but path goal cannot add a cell, because if you do like path goal equal to cell, then you'll keep count the duplicate. I mean, you will overlap every single time when you're trying to traverse the basically traverse 4 different directions. So you don't want to add the a value over and over again, right? So let me run it. Yeah, so again, you can see that this is more efficient because I stop the the traversal right here, and also I stop the traversal right here if I have all of the gold. So the time will be the same, all of n times m, and this is all of 4, and this will be the worst case going to be all of n times m. But again, this condition, in average, it will optimize the solution. But the space, let's think about the space. So this is space, and then space, this one and this one. So this is constant, and this is all of n times m for the time, and then that's pretty much it. So this solution is better, but it will be hard to think about this condition. So this is everything, and then I hope you get it. All right, see you.